Sequence of numbers. In this video, we define what we mean by a sequence of numbers. We will focus on how to find the formula for the general term of a sequence and what it means for a sequence to converge or diverge. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. A sequence of numbers is just a list of numbers. For example, here is a list of numbers. When the sequence goes on forever, it's called an infinite sequence. Otherwise, it is a finite sequence. We will be dealing exclusively with infinite sequences in this video. The dots signify that the list keeps going and going and going forever. Each number in a sequence is called a term of that sequence, and it is common to represent sequence by subscript notation. For instance, in the sequence, the first term is 2, and we can write a sub 1 equals 2. The second term is 4, and we can write a sub 2 equals 4. The third term is 6, and we can write a sub 3 equals 6, and so forth. The expression a sub n is referred to as the general term of the sequence. The n stands for the term number. This sequence is infinite, so we suppose that the sequence continues by following the pattern that the first few terms suggest. It seems natural to seek a formula that describes this sequence. These terms are multiple of 2, so we can state a rule or formula based on n. This sequence can be represented as 2 times n, where n is a positive integer. You should keep in your mind that the sequence does not have to start at n equals 1, but may start at n equals 0, n equals 2, or any other positive integer. We can write the nth term in the sequence by the explicit formula a sub n equals 2 times n, or the nth term is 2 times n. Notice that for every positive integer, there is a corresponding number, and so a sequence can be defined as a function whose domain is the set of positive integers. Sequences are written down in a few different but equivalent ways. From now on, we will use the last notation. This discussion leads us to the following formal definition of a sequence. A sequence can be regarded as a function with domain as the natural numbers and codomain as the real numbers, such that f of n equals a sub n. The range of the function is the set of all distinct values of a sub n. The terms of a sequence are the values a sub 1, a sub 2, and so forth. Sometimes it's a good idea to list the first terms of the sequence to make it clear how the general term works. To get the first few sequence terms, all we need to do is plug in values of n into the formula given, and we will get the sequence terms. Let's see how it works. The general term for item A is n squared, or the nth term is given by the square of the number n. To find the first term, we substitute n by 1 and multiply 1 by itself. To find the second term, we substitute n by 2 and multiply 2 by itself. To find the third term, we substitute n by 3 and multiply 3 by itself. The dots tells us that the sequence continues on and doesn't terminate at the last term. Look at item B. The terms in the numerator are always powers of 3, and the terms in the denominator are given by n factorial. The general term for item B is 3 to the power of n over n factorial. This sequence starts at n equals 0. To find the first term, we substitute n by 0 and perform the calculations and simplify. To find the second term, we substitute n by 1. To find the third term, we substitute n by 2, and so forth. Sometimes we are given the first few terms of a sequence and asked to find a general formula for that sequence. Before we go any further, here are 4 basic rules for finding the general term of any sequence. Match the terms of the sequence to their place in the sequence and find the pattern that relates each term to its corresponding value of n. If the odd terms are negative, a sub n will include minus 1 raised to the power of n. If the even terms are negative, a sub n will include minus 1 raised to the power of n minus 1, or minus 1 raised to the power of n plus 1. Let's look at 2 examples. We are looking for a pattern of some sort. First, match the terms of the sequence to their place in the sequence n, and then find the pattern that relates each term to its corresponding value of n. Look at the numerator. What do the numbers 1, 2, 3, and 4 have in common? We see that each numerator is the same as the index, starting with n equals 1, without regard to the sign. Next, consider the sequence of denominators. The denominators are the third powers of the positive integers, starting with n equals 1. We also should notice how the sign changes from term to term. As this sequence has negative even terms, we will multiply by minus 1 raised to the power of n plus 1. Thus, our formula is given as follows. Look at item B. First, match the terms of the sequence to their place in the sequence n, and then find the pattern that relates each term to its corresponding value of n. Look at the numerator. What do the numbers 1, 4, 9, and 16 have in common? They are perfect squares starting with n equals 1. Next, consider the sequence of denominators. It may appear difficult to find a pattern for the denominators. Let's look carefully at the second and the fourth terms. The denominator of the second term seems to be its numerator minus 1, and the denominator of the fourth term seems to be its numerator minus 1. We should notice that 4 squared is the same as 2 raised to the power of 4. Now we could ask ourselves, does this formula also match to the other denominators? Let's check. The denominator of the first term is 2 raised to the power of 1 minus 1. And the denominator of the third term is 2 raised to the power of 3 minus 1. As we can see, additional checks show that this formula does indeed match the other terms in the sequence. Two types of sequences occur frequently and are given special names. arithmetic sequences and geometric sequences. If you want to study these two popular families of sequences a little more, you should watch the two videos that appear in the upper right corner of the screen. The main question that arises regarding infinite sequences is what happens to the terms as n gets very large. In short, what happens to the nth term when n goes to infinity? When n goes to infinity, the sequences could have three types of behavior that we shall wish to describe explicitly. These are sequences that tend to a real number. We can see that the terms of the sequence are approaching a finite number as n tends to infinity. So we say that the sequence is a convergent sequence and the real number is the limit of the sequence. A convergent sequence has a limit, that is, it approaches a real number. Sequences that tend to minus or plus infinity. The sequence grows without bound, rather than approaching some finite value as n tends to infinity. Then we say that the limit does not exist and the sequence is divergent. Sequences that behave in some other way. The sequence oscillates between -1 and +1, rather than approaching a single value as n tends to infinity. Then we say that the limit does not exist and the sequence is divergent as well. A divergent sequence doesn't have a limit. Since a sequence is a function defined on the positive integers, it makes sense to discuss the limit of the terms as n goes to infinity. The limit of a sequence is the value the sequence approaches as the number of terms goes to infinity. We can give an informal definition of the limit of a sequence. The limit of a sequence a sub n is a number L such that the terms a sub n remain arbitrarily close to L when n is sufficiently large. That is, the limit of a sub n as n approaches to infinity is L. If this limit exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. Because a sequence is a function whose domain is the set of positive integers, we can use properties of limits of functions to determine whether a sequence converges, and we can write the definition above as follows. Let's take a look at a couple of examples of limits of sequences. When we have a polynomial divided by a polynomial, we identify the highest power of the variable in the denominator. We divide both the numerator and the denominator by the highest power of n. Cancel and then take the limit. So the sequence converges and its limit is 1/2. To solve item B, we identify the highest power of the variable in the denominator as square root of n to the power of 3. So we divide both the numerator and the denominator by the highest power of n. Cancel and then take the limit. After some algebra, we can see that the limit does not exist and the sequence diverges. we need to be careful with this sequence. This is an oscillating sequence, so we could think of it as divergent. But let's calculate the limit and see what happens. The limit is zero regardless of the oscillating term. Now, taking into account the oscillating term, we realize that the limit of the sequence is always zero. So, this sequence is convergent. Here we go through an oscillating sequence again. Basically, we will do the same as the previous example. Let's calculate the limit and see what happens. The limit is 1 regardless of the oscillating term. Now, taking into account the oscillating term, we realize that the limit of the sequence bounces around 1 and minus 1. So this sequence is divergent. As with limits of functions, there is a squeeze theorem for the limits of sequences that is another tool that can be used to determine whether a sequence converges. The squeeze theorem for functions can also be adapted for infinite sequences as follows. This theorem allows us to evaluate limits that are hard to evaluate by establishing a relationship to other limits that we can easily evaluate. Let's see a couple of examples. We want to apply the squeeze theorem by squeezing the sequence given between two sequences that converge to the same limit. To apply the squeeze theorem, we need two functions. One function must be less than or equal to the nth term, and the other function that we must choose must be greater than to or equal to the nth term for all n. So we know that 0 is less than or equal to the nth term. We now expand the sequence. We can see that each factor in the first product is greater than or equal to 1. Then this product is greater than or equal to 1. On the other hand, we can see that if each factor in the second product is less than 1, then this product is less than or equal to 1. If we lump together the first factors and call the product C, and drop all the remaining factors except the last factor, 8 over n, we can write the following inequality. We now can apply the squeeze theorem to find the limit of the sequence, and the sequence converges to 0. Keep in mind that we want to apply the squeeze theorem by squeezing the sequence given between two sequences that converge to the same limit. We know that n to the power of 4 is less than n to the power of 6. So we find a sequence that is less than the original sequence by replacing n to the power of 6 with n to the power of 4. And we find a sequence that is greater than the original sequence by replacing n to the power of 4 with n to the power of 6. We now can apply the squeeze theorem to find the limit of the sequence, and the sequence converges to 0. The trick here is to identify the strongest term of the sequence. The strongest term here is 5 to the power of n, because for large n values, the other terms are tiny, as if they were not there at all. So to find a sequence that is less than the original sequence, we omit everything but the strongest term. On the other hand, to find a sequence that is greater than the original sequence, we replace all terms with the strongest term. After some algebra, we take the limits and apply the squeeze theorem, and the sequence converges to 5.